A protocol is a set of rules that are implicitly or explicitly followed by any two entities that wish to communicate. So, as an example, suppose you want to talk to a friend. When you see your friend, you might say something like hello, and then the friend replies hi. And in that case, it is clear that both of you wish to communicate with each other at this time. On the other hand, if the friend happens to be busy, they might say something like, oh, I'm in a hurry, and walk away. This kind of implicit social rules governs all communication, at least amongst people. And then there are more complicated versions of these. For example, how one should address a dignitary like the president of a country or a chief guest at a function and things like that. We are so used to it that we don't always realize how arbitrary these rules are. But over time we get used to it. Now similarly, the issue replicates itself in the case of computers. If two computers wish to talk to each other, but one of them is busy, what are they supposed to do? This is the reason why computers also have protocols. The particular protocols that we are interested in are IP, TCP, and HTTP. IP stands for Internet Protocol, and as such, it is the core protocol that defines pretty much what it means to be the Internet. As an example, the core functionality of what we call the Internet is to be able to identify a computer and somehow reach it. This job is done by IP. Here, reach has a very specific meaning. Reach means something like, can I send an envelope containing certain data, which is known as a packet, to another computer, specify its address somehow, and some machinery should exist which takes this packet from this computer to that computer. That job is done by IP. And so we can say that IP is the protocol that defines or establishes the Internet. IP is what is called a datagram protocol or a packet protocol because all it does is it sends chunks of data. Now on top of this, we use another protocol, TCP, which defines something called ports, which we have seen before just now. So a port is a service that can exist on a machine, that represents a service that can exist on a machine, and a TCP, an entity which wishes to speak with a TCP port on one side, will be able to establish a connection with another entity with a port on another side. And then once the connection is established, you can send packets of information that to the user of the connection feels like a continuous data stream. So using these protocols, we can further establish communication rules such as HTTP and FTP and many others that put additional constraints on just what kinds of messages can be exchanged. This sort of set is considered to be a protocol. When multiple protocols cooperate in some fashion, they are said to be layered. Here, layering has a very strong analogy with how any communication facility must work. So for example, HTTP or FTP over TCP is a bit like two different human languages which are layered on top of our core ability to emit and hear sound waves. So in this metaphor, TCP is equivalent to the mouth and ear mechanism, which allows us to exchange just sound waves, some kind of sound. The next layer up over this core biological functionality is things like languages like Sanskrit or Marathi, which invent their own rules by which people can talk to each other. So the analog is to HTTP or FTP, which is file transfer, and SMTP, which is the email protocol. SMTP stands for Simple Mail Transfer Protocol. So these protocols are like higher level languages on top of basic ability to make and hear sounds. One characteristic of such a mechanism is that it's very much like the way we structure programs using functions. There are general purpose functions which are used by special purpose functions. Similarly, the special purpose protocol TCP uses a more general protocol called IP, and in turn HTTP, which is a still more specialized protocol, uses the general protocol called TCP. Okay, so that's as far as the layering goes. The next part is to notice one other thing about this kind of layering of languages, which is that clients and servers must both speak the same language in order to be comprehensible to each other. So the analogy here is that although all people can hear sounds, or well, let's say most of us can hear sounds, two people communicating with different languages cannot actually communicate with each other, and it doesn't matter whether they can hear the sounds emitted by each other or not. Those sounds have no meaning. So in this sense, a FTP client cannot talk to a HTTP server. You might expect that, say, strictly speaking, a HTTP client cannot talk to a FTP server either. This is true. On the other hand, browsers can talk both HTTP and FTP. And this is because browsers are multilingual, universal clients, as we will discuss shortly. Browsers, in the sense that we have just discussed, can speak multiple languages. Here are a few examples. I have shown two sites for a service called CTAN. CTAN is short for Comprehensive Tech Archive Network, which was one of the earliest successful users of FTP and HTTP servers since the early days. So it stands to reason that that kind of service with its long duration still offers both FTP and HTTP access to the information. And as we will see in a short while, and you can go and look it up yourselves, these two services show the same data with two very different interfaces. As another example, browsers can also look at the local file system. So we say that browsers are file system clients. Something like file C users on Windows is a URL for the local file system. Browsers used to support still other protocols. An old protocol, one of the early protocols on the internet, was something called Gopher. And for a long time, browsers supported this protocol as well. So what browsers did was they became a gateway from any protocol to, in effect, the world of HTML and the web in general, which is why we make a distinction between the internet and the web. The net is the net, which is defined by things like TCP and IP, whereas the web specifically is largely about browsers and HTTP servers, although there are ways to adapt to the older world and different services like FTP. Gopher, for instance, is now nearly extinct, except for a few servers and browser extensions which are maintained largely by hobbyists. What the browser does is, for every kind of data that it gets from a server, it converts that effectively into HTML and then displays it. But it is not the case that the browser can display everything. In the old days, browsers, even for PDF files, used to launch separate programs on the local desktop. However, nowadays, browsers have PDF readers built in. Still, that's not true for every kind of URL. The URL mail2xyz, which is also a URL by the way, is a case where if you click on it, the browser will launch an email program instead of displaying the resource because there is nothing to be done. Thus far, at least, browsers haven't evolved to become email clients in the sense that the Mail2 protocol wants it to, even though, as we know, browsers make excellent mail clients. For whatever reason, the Mail2 protocol has never been combined, probably because it requires local desktop information or something. Let's take a look at the examples we just discussed. Here, for instance, is the website ftp.henet.ie, which is accessed as a HTTPS service. And as a result, we get a normal HTML page which shows you what the contents of this thing are. Now the same information is available on also from ftp-henet.ie, but with the FTP protocol. And as we see, the presentation here looks much more like an ordinary file system compared with the nice HTML layout that we have seen. But here is something interesting. The HTML layout that we have seen is usually available in a file called index.html. So here, when you look at HTTPS for this resource, implicitly this thing is fetching a file called index.html. You don't have to say it. That is one of the things that is automatically done by servers. But let's try to fetch it ourselves from the FTP server and see what happens. So here what happens is, now this is behaving like a HTTP server, and as far as as a FTP server, and as far as Firefox knows, this is a FTP service. So at this point, it doesn't know what to do with index.html, because if it were getting it from HTTPS server, there is an indication that says what to do with it. Here though, Firefox does something interesting. It says, I'm trying to open index.html. I don't know what to do with it since I got it from a FTP server and the indication isn't there. But then I do know that .html files can be opened by Firefox. So should I open it with Firefox? Strange as it seems, this is quite logical. And if you say yes, by all means go ahead and open it, as you can see, it gets a local file here on my machine. And that file, because it is the same HTML file, looks identical to the file to the web page that you see here. So this is what happens. This is the interesting example which shows you a distinction between a HTTP server and a FTP server. Implicitly, we have also seen the browser work like a file system information retriever while doing this work. For example, here is the actual file get from the file : a temporary directory. But because it happens to be a HTML file, Firefox knows what to do with it now for display purposes, because it is retrieved from the file server rather than from an FTP server. So for the file server, there are rules that say what to do with a HTML file, but for the FTP server, there aren't. We could, but right now there are not such rules available. And now if you go back and look at some other example, for instance, here is my XAMPP installation, then you see this is just like a ordinary sort of file system. And if I click in CGI bin, I can see some examples of the programs that we have written so far. So this is how a browser works as a universal client. These examples show us that the features we experience as users of the web are because of interactions between server features, browser features, and protocol features. Our first example was that when you visit a URL that is basically just a directory URL, the server implicitly shows the contents of the file index.html at that URL if it happens to be present. Just like this, browsers will also have features, and user options chosen by the users among the browser settings will also contribute to some implicit behavior. For instance, retrieving index.html over HTTP versus FTP led to a different behavior. The browser could have chosen to hide it, but either Firefox doesn't do it, or I have myself set some behavior which prevents that from happening. I no longer remember, but since FTP is so rarely used, this particular behavior doesn't matter much. So that gives us another choice. This choice happens to be done in the browser, but as far as the user is concerned, they don't care. When doing web development, we need to build within ourselves a very clear understanding of all the different ways in which a particular feature could be achieved. You have to be aware of what kind of server you are getting it from, what are the settings the server is telling us about, how is the browser interacting, and how is the user interacting with it. This adds to the difficulty of web programming. But again, as I said before, after a while you get used to it, and the culture around us plus things like Stack Overflow help us figure out what is really going on. Tricky bugs can occur due to interactions between browser makers' choices, user choices, and protocol related header configurations, server configurations, and an endless number of other things. It's useful to remember that these distinctions exist and over time build up a clear understanding of what is the root cause for a particular effect. We have seen that protocols exist in order to allow communication between different entities, and that they are layered so that we can divide the responsibility of different parts of communication among different protocols. But the specific layering we care about most is the layering of HTTP over TCP. Relative to HTTP, TCP is the low-level protocol that establishes and terminates client-to-server connections. Once TCP establishes a connection, a client that can speak HTTP will send specific TCP messages that bear a format which is known as the request format. We say that a TCP server is a HTTP server if it recognizes the request format and replies appropriately in the response format. We can use our earlier analogy of sound and language to understand what is going on here. Every human speaker uses sound waves, but if the waves have a specific shape, then we are capable of recognizing it as a particular language. So it is with TCP and HTTP. If the content of a TCP packet is of a particular kind, then a HTTP server can recognize it as a HTTP message and respond appropriately. So the response format in turn tells the client that yes, it succeeded in talking to a HTTP server and the response it gets is an HTTP response. Protocols are all well and good, of course, but before computers can communicate, they need to be able to address each other. This job is done by the system called domain name system and the IP addresses which constitute the names of the machines that need to talk to each other. So this job, the DNS's job, is a map of domain names to IP addresses. An IP address is a 32-bit in the case of IPv4 or 64-bit in the case of IPv6, a number that helps locate a server using IP routing. The routing mechanism actually shares some features with geographical route finding algorithms like in apps like Ola and so forth, Zomato and whatnot, which help tell drivers how to go from here to there and keep track of things like how much congestion is there and so forth. Route finding in the internet is surprisingly similar. When you type a URL, the browser determines the IP address of a hostname. You don't need a browser to do the lookup. NSLOOKUP is a small program that is used to find out the IP given the hostname. You should try this out on your own. I'll give you some examples below and indicate what it is that you are seeing. So, if you look at nptel.sc.in, here we have the results of using NSLOOKUP on this site. It may not always, I have cleaned up some of the irrelevant stuff, and the part that matters is the name address pair nptel.ac.in and the IP address that you see. Similarly, if you try NSLOOKUP for apache.org, httpd.apache.org, then again you see this name and the addresses. The long address here is of IPv6 style and the other two are the old IPv4 style. You may not always get the same IP addresses. There are mapping mechanisms which distinguish between a domain as approach from India, for example, versus a domain as approached from, say, Japan, and you may actually end up seeing a different IP address depending on how the site has been constructed. Nonetheless, the bottom line is that as far as the user is concerned, you see the domain name, you find the IP address, and your expectation is that whatever content anybody in the world sees at that domain name is also the content that you will see. As long as that happens, it doesn't matter. Some mapping should exist. That's all we care about. So, once that is established, we can now, TCP can now establish a connection and packets can be sent. After DNS helps us find the IP address, TCP's job is to ring up the other computer and establish a connection. Once a connection is set up, then we can exchange HTTP messages over TCP. An HTTP message is the data conveyed by the underlying TCP messages. This is much like putting some content inside an envelope and mailing that using the postal service. In turn, an HTTP message conveys its own data, such as user input from forms, responses from servers, and so forth. And it itself has a similar distinction between the information that is used for the purposes of the protocol versus the information that is used for the purposes of the content. We will see that in a little bit. This is known as the header versus data distinction. When we begin speaking with one another, we might say some word like hello with a response such as hi. These two words, hello and hi, strictly speaking, are fillers. They are not relevant to the communication or the data that is going to happen next. Their role is simply to establish that the preconditions for talking about something are met, that the relevant amount of interest is there. This information is known as header information. And the actual thing you want to talk about is the data. So the analogy here is address on envelope versus the contents of the envelope. Let's see how in our protocol stack, since protocols are layered on top of each other, we call the end result a protocol stack. So our protocol stack has IP at the bottom, TCP inside IP, and HTTP inside TCP, and finally HTML data of the sort we want our users to see. The details look a bit like this for IPv4 at least. First, the header, which is the hello, so to speak. I haven't shown the entire header, I have only shown some relevant pieces of it. This header says that the first 32 bits are the IP address of the destination, which is used by the routing mechanism to take the packet from your computer to the destination computer, or so to speak, from the browser computer to the server computer. It carries the IP address of the source, which is the originator of the communication, so that the other side can reply back. There is a third header called time to live. This shows up in interesting ways, so I thought I'll mention it. However, we won't be spending any time describing this header. Okay, now inside the packet, there is the data part. This data part, for the case of TCP, contains a TCP message. In turn, the TCP message has a TCP header and a TCP data distinction. In TCP, you have the source port number, you have the destination port number, you have a sequence number. Since TCP is a stream of data, it sends packet in a sequence, and these sequence numbers help tell us the order in which packets should arrive at the other end. If packets become out of order, TCP is capable of waiting and reassembling your stream in the order necessary. Now, since we are only interested in using TCP and HTTP combination, we will say that as far as our messages are concerned, the data part of TCP consists of HTTP packets. What's an HTTP packet? Again, there is a header and there is data. Now in this header, in contrast with the headers of IP and TCP, You will notice that the earlier two headers are defined in terms of bits, but the HTTP header is defined in terms of text. So this switch from bits at the low level protocols, which are all largely about efficiency, versus text at the higher level protocols, is because it's simpler for the developers of the higher level protocol to develop these kinds of systems rather than complicated systems involving bits and so forth. Not that that really prevents us from getting to bits if we really want to, and nowadays people do, but let's leave that aside. Let's just say that our HTTP packet has this kind of header. Now, the word get here is exactly like saying hello, at least in the sense of what it achieves. It tells the receiver that the sender wants to get this particular URL using the protocol HTTP 1.1. So when I say get is like hello, what I'm saying is the packet is prefaced with the word get, and that prefix tells the receiver that this is a HTTP packet. That's not the only thing. You also need to end the first line with this line HTTP 1.1 or 1.0 as the case may be. Just like there are addresses in the IP and TCP packets, there is an address here which is the hostname.com. And there is a third header I have shown. There are many more headers and we will talk about it in greater detail later. But for now, I have shown one more header called content type. So if the content type is text HTML, then the data part should be HTML. That's what it means. This is not the only kind of content. The other kind of content which we will commonly use is text plain, in which case the received message is simply plain text data. There is no HTML or anything as far as the browser expects it. Now that we have some idea of what protocols and the messages that they send look like, let's use this understanding to get a greater grip on how HTTP works. So our first step here will be to say that we are not interested in the details of IP and TCP, but we are interested in the details of how HTTP messages are built up using the baseline of TCP and IP. Therefore, we will use a ready-made program called SOCAT, which already knows how to speak TCP, and we will use this program to build HTTP clients and servers. Of course, our clients and servers are just enough to illustrate what is going on so that you have a good grip on what it means for some interaction to use a HTTP protocol. So let's take a look at SOCAT. SOCAT is a general purpose gateway program that acts as a bridge between normal machine standard input and standard output and TCP ports. We will look at these examples, and after we are done with these examples, we will see a demo in which you will see how this overall setup works. SOCAT can act as a TCP server. So we say that a server has to sit and listen. It listens for requests, and whenever there is a request, it responds. It receives messages from remote TCP programs, and depending on what the server is designed to do, it will further interpret the data that it receives from the TCP programs and then will send whatever output we want back to the program which interrogated it. So let's take a look at some basic examples here. The lines below show you a simple server that waits for a client, sends one message, prints it, and then terminates. What is happening here is that the program echo sends the word goodbye to the input of this particular SOCAT instance. This SOCAT instance says the dash here means listen to the standard input, and this command TCP listen :8001 says that listen for any TCP communication on port number 8001. Now in another terminal, we will create a client which also uses SOCAT. The job of the client is to say hello to the server at port 8001. So here we say echo hello and send that as input to SOCAT. This SOCAT is also configured to listen to its standard in, but this time what it says is talk to TCP on localhost at port 8001. As soon as the client runs, the server will receive the message hello from the client and it will terminate because this is just a one line and there's nothing else to do once the message is received. In turn, the client will receive goodbye from the server because that is what is available to the server on its standard input. And again, because there is nothing more to do, the server will terminate. Now let's see how this works. Here in the left-hand window, we have set up the server. This server will receive the goodbye message and it will listen on port 8001. The dash, as you can see, says to SOCAT that what it should do is to get the messages that it receives from the standard input and send them to whatever the other endpoint is. Similarly, here on the right side, we have the client. Here, SOCAT receives a message from standard input and sends it to wherever the other endpoint is. Let's start the server first. Notice that the server is just hanging waiting for input. There is nothing for it to do. That is the very nature of servers. If they are not busy, they just sit around doing nothing. Now let's start the client, and what you will notice is that the processing is fast enough, of course, that as soon as the message is received, both of these appear to terminate at the same time. But what is happening is that the client is first sending the message, then completing the reception of the message from the server, and then the system together is coming to a halt. There we go. The goodbye message came from the server to the client, and the hello message went from the client to the server. Oh, by the way, this is on a single machine, but it doesn't have to be. Wherever, if you have access to multiple machines, then by all means try this out on multiple machines where you can open ports, and you will find that this program will work just fine. Now that we have seen the basic behavior of SOCAT, going forward we will focus on HTTP. We will take TCP and IP for granted, and in the following we will see how SOCAT can be used to build toy HTTP clients and servers. And later we will study other more built for HTTP tools like curl and Firefox web tools. The transition from using simple tools like SOCAT to build HTTP clients and servers will show you that how the layering actually works in practice. But a normal web programmer will rarely need to use things like SOCAT except on very special occasions like proxying and tunneling and so forth. But aside from those unusual TCP related uses, the usual tools that we use will be curl and Firefox, like Firefox web tools type things. So let's take the next step and see what happens. Let's get started with the HTTP protocol. The oldest, simplest form of the HTTP protocol was version 1.0, which had a very straightforward implementation. A client, the browser, opens a connection to the server, sends its request, and once it gets the reply that it wants, it terminates the connection. This kind of simple implementation made it very easy to get started with the web. The software was dead simple, and long ago when machines were not so powerful and people were not so used to dealing with massive amounts of software with IDEs and great debugging and so on, it was important that the software be simple. As the web became more popular, it was then at that point easy to say that, oh, we want better performance, and so we should be using we should not be establishing connections so often. So modern HTTP protocols from version 1.1 and above maintain a single underlying TCP connection. They can exchange multiple HTTP messages over a single connection, just as we don't really stop a phone call, let's say, after a single sentence, but we will wait for some acknowledgement from our listener and then continue on to the next. Something similar happens in the case of multiple HTTP messages over a single TCP connection. Here is a technical terminology piece that you should know about. Whenever a single connection is shared for multiple HTTP interactions, it is called a persistent connection. And remember what I said about starting simple? In general, it has been the experience that when you start with a simple system, wait for some amount of popularity and then increase the complexity, such designs turn out to be more fit for survival, let's just say, as different requirements get put on these systems. Okay, now we are going to look at the details, and for that, let's first make sure that with the ordinary browser we can get some results, and whether we can get the same results by using SOCAT and other TCP oriented tools. So here I have XAMPP, which I have started, which is running Apache at port 80 and 443. And here I have a browser. This browser shows you what you see when you get the localhost domain. And like I said, browsers for whatever reason have started dropping the HTTP prefix. So we don't see that anymore, but nonetheless, this is what we see. I have made some changes to the default XAMPP setup. There is a file called index.php in this directory in default XAMPP, which I just completely removed. This then drops the behavior of the system to the native behavior of Apache, which is to simply show the underlying file system. Similarly, you can see the results when you look at a domain like www.example.org versus just example.org, and the result is exactly the same, which is what we expect. Now what we are going to do is we will see how to get similar results without a HTTP client of any kind. We will use TCP clients like Telnet and SOCAT to talk HTTP. Another alternative, Netcat, is available, but there are too many incompatible versions of Netcat on different operating systems. Therefore, we use SOCAT, which is more predictable across different systems. So let's write our first HTTP request manually. The beauty here is that you hardly need any software because the protocol is defined as a text protocol. Because the protocol is defined as a text protocol, it is very easy for us to just type in and get the results we want. So let's just do exactly what the slide says. Telnet localhost port 80, and we have connected to the localhost. Now we can say get /http/1.0 followed by an empty line, and now you see a large amount of HTML that the system sends you. This content is the same as what we see here, although it's a little bit harder to see because, for example, I'll show you here. So XAMPP shows up, Webalizer shows up. So all the content is the same. It's just that there is a bunch of HTML that is visible, which the browser nicely renders into this kind of a list. So that's our first example of HTTP protocol. Now let's try this one. Here what we will do is we will use SOCAT. So printf get /http/1.0/r/n/r/n. The first /r/n terminates the HTTP 1.0 line. The second /r/n terminates the empty line that is supposed to occur after the first line. And now we have SOCAT minus TCP localhost 80. There we go. The same thing. When working with these kinds of systems, it is important to know exactly what data you are going to be sending. So let's see what the difference is between things like printf, echo, echo minus e, etc. Here we have this line with printf, and od is a dump command. So let's see what bytes actually get sent. So we have get, etc., space slash blah blah blah, followed by /r/n, which is exactly the bytes we sent. On the other hand, suppose you had used echo, then notice if you compare these two lines, you will see that instead of a single /r/n, you see one slash then a r, one slash then a n. This is not the same thing. If you want that back, you would have to say echo minus e, and even then there is a difference, because while you get the /r/n, etc., there is an extra \n that is tacked on at the end. This may or may not matter, but because it may, we will use printf because it sends exactly what you typed, no more, no less. Sometimes instead of od minus c, which shows you the characters, it is useful to have hexdump so that you can take a look at the hex codes of the bytes you are sending. And here we go. So if you do this, as you can see, hexdump shows you these bytes. Let's try and make this a bit bigger and easier to see. So the standard style of hexdump is to include the hex codes followed by the characters on this side. This is sometimes easier to understand than the dumps produced by OD once the sizes get bigger. With this, we have our first HTTP client built using nothing but the underlying TCP systems. So just to clarify, let's take a look at this again. And as we can see, the same kind of thing is showing up here as you can see here, except of course with the browser it looks a lot prettier. Now let's do the same thing, but for the HTTP 1.1 protocol. So here we go again, localhost 80, and we have get/HTTP 1.1, and this time the next line has to be this, followed by connection close. And here we go. We have our XAMPP back again. Let's do the same thing again, but this time with search to see if I have already printed this somewhere before so that it's not that complicated. Let me change this to localhost connection close and so cat minus TCP localhost 80, and there we go. So the distinction between HTTP and HTTP, 1.0 and HTTP 1.1 is in what lines should be allowed as the header. One novel thing is that the host must be mentioned, otherwise it is not a well-formed packet. The processing of HTTP 1.1 is somewhat more strict. So let's say what happens is we try this, but then you make a mistake. You say HTTP 1.1, but do not include the host line, let's say, and just do return afterwards. What you'll see is this kind of message. Your browser or proxy sent a request that this server could not understand. So in this sense, HTTP is stricter. One other thing we'll get to later is that there's another form of error which shows up in the protocol itself. It says HTTP 1.1 400 bad request. This means that you made a mistake somewhere in the request. If you compare this with what happens if you do the correct sequence, then what you will find is localhost connection close. Now here the protocol tells you that things are okay. HTTP 1.1 200 okay. 200 is the code for okay. The last distinction that we can do compared with 1.0 is that persistent connections are taken to be standard. So we have to say connection close, and if we don't, then what happens is that the connection remains open. So let's see. So here, as you can see, you can the server hasn't given, the client hasn't stopped being connecting to the user, but now you got a connection closed by foreign host. So what is happening here is that the client doesn't want to close the connection. The server sends the message back, the server sends a response back, and then it says, if I don't receive anything from the client until after some time, then I'm going to use a timeout, and after this time I'm going to close the connection. So in this sense, persistent connections have a timeout at the server end so that empty connections are not unnecessarily maintained. But the main point is that unlike 1.0, connections explicitly have to be closed, either that or they will be closed because of timeouts. Okay, now let's look at the next part. Now we can do something more interesting. We are going to use a socat command to create a server, but this time our server will listen on port 8090 or 8001 or whatever it is you want, because port 80 is already occupied by Apache. So let's see what it is like to write a server using socat. Here we go. So let's go ahead. For I in 1 to 10. So 1 to 10 is here just to close the server after 10 requests are done. Is there any reason for it? Not particularly. We just don't want an infinite loop, because killing infinite loops gets a little tricky sometimes under Cygwin and things like that. So I'm automatically closing the server after 10 requests. But here is our server. So printf http 1.1 200 okay. So we are always going to send okay no matter what, as we already saw how the server sends okay. So this is the first part, and the second part is printf a tab hello client server here on date. So we will print the date, followed by again /r/n, and complete this thing. You have that. Pipe this into socat minus tcp-listen 8090, and finally we have done. Okay, so now the server is waiting. Now let's see what happens on the client side. So on the client side we have echo hello socat minus tcp localhost 8090. There, our hello went to the server, which printed it out, and our server sent back HTTP 1.1 200 okay, followed by this hello client message with a date. We can do this again. Let's say hello again, and we'll create some space here to separate out the different responses. And now let's do this again. So same thing, you got a hello again. Now let's try connecting to our server with a browser. So here we go. Instead of localhost, we will say localhost 8090. Here, the browser gets this message back, hello client, server here. And on this side, you see something much more complicated. So this is the hello again from the previous connection. Let me do this again to make it very obvious. Okay. So here is what we get. We are getting, in the first case, you got a get HTTP 1.1, same like here. Host, localhost, user agent. So user agent tells you which kind of browser is asking. The bunch of other headers which we will look at later, and so on. The first time, there is one more request that happens to get the favicon, which is one of those little icons, like for example this one, which decorates the tabs in web browsers. And that request gets automatically made. It turns out that there isn't a fav icon because we don't serve one, and so next time the request is not repeated. So as you can see, as far as the browser as well as this client is concerned, the server appears to be a valid HTTP server. Now, there are limitations here, of course. One thing is that our server replies with the correct HTTP response format, but it doesn't verify that the input is a HTTP compatible message. So although the browser sent a correctly configured HTTP message, our other client, the one over here, did not, and that was perfectly fine with this particular server. Nonetheless, you can see what the basic idea is. A server listens to a message and then sends some formatted text in response. And with not much effort, with the aid of a TCP program, we have a working HTTP toy server and a HTTP toy client as well. So the key issue here is to consider the sheer simplicity of HTTP. The basic idea is dead simple. On top of TCP, you layer a standard way to send requests and responses. And so, given some way to handle TCP connections themselves, doing HTTP on top is very simple. Let's correct this to HTTP. Okay. Web servers like Apache and Tomcat share the same underlying structure as our toy servers. They listen to messages in HTTP format and they respond. Now we are going to look at what each of those lines in the protocol headers actually means. This is part 4, HTTP details and web tools. We will begin by studying HTTP headers, followed by a study of curl and Firefox web dev tools.